a representation of gradual change, and the method would not be appropriate were the change to have come about because somebody put in a point source control at a very specific point in time. It would tend to smear it out. And we can describe, and this is exactly what's been done by the USGS and presented to the community of managers in the Chesapeake Bay watershed, that the change at this particular site from 2005 to 2014 is a change from about 3,800 kilograms per year to 5,700 kilograms per year. That's our estimate of the change. We do this at many sites, we do that, and we look at various time periods and various constituents of interest to the Chesapeake Bay system. We can also look at the uncertainty of that using a bootstrap methodology that we've published and have coded up for people to use. This is one example of the output of that, which is to say our estimate of the change from 2005 to 2015 was that it was a 54% increase, but we know that number is imperfect. This is very noisy data. There's a lot of complexity. The bootstrap method says, well, you know, the fairly likely range of that increase is anywhere from, say, 30% up to about 70%. But what we can say is the probability that the true change is actually in the negative direction is virtually zero. We can give this probability distribution of what the change is. This story I've just told you is very much in contrast with what the models used in the TMDL have shown. They assert basically that orthophosphorus should be declining because of the particular farming practices undertaken. This analysis has helped to show how flawed that is. And this empirical result is a wake-up call about an emerging problem in the region. This, again, is this interplay between empiricism and modeling that we always need to check to see whether the system is really behaving the way that we think it is. One real quick story from an area in New England. This is chloride trends. This is a work from my colleague John Mullaney in the USGS Hartford, Connecticut office, looking at chloride in a river in the Hartford area from 1990 essentially to the present, and it's on a logarithmic scale, and the chloride concentrations have undoubtedly increased. And this is a widespread phenomenon over all the parts of the United States in which there's extensive snow and the use of chloride of road salt to remove it. This is the WRTDS model of this system, and what you see here is that the increases are particularly happening in low flow where there's relatively little dilution. And it's not just happening in the wintertime, it's happening throughout the year. This is an example. This now is concentration of chloride using the same methodology that I described before, and we see it marching upward from an average, and but it's only the wintertime, December, January, February, March, marching upward from 30 milligrams per liter to 90 milligrams per liter over this period of time in that season. But we can also look at the summertime, July, August, September, October, and what we see is it's also marching upwards over that time, not quite as rapidly, but still very much so. Ecologically, this may be a more important issue than the wintertime change in concentration because it may have more severe biological implications during this time rather than in the winter when the aquatic biota may be dormant. I'm going to skip over, and this is just a statement about the software that we have developed that does many of these analyses you've seen, the Egret software, another package called data retrieval, which allows you to grab any kind of data from the USGS records, doing it within inside the R statistical package, and bring it in to make it available for use. It really saves a lot of time and difficulties, and all these are available from CRAN. So back to sort of where we started this whole presentation, stationarity is dead, wither water management. One of the statements in that paper is, in a non-stationary world, continuity of observations is critical. Some of my colleagues, when I started working at the U.S. Geological Survey, were of the viewpoint that if you want to do something like characterize flood frequency distributions or distribution of daily stream flow, if you collect about 30 years of data, you may have a good enough estimate of the mean and of the standard deviation and the quantiles of the distribution, and you can go and you could start measuring in other places and try to get an understanding of how it changes from place to place, because if it's stationary, you can get a pretty good handle on it. in a recognition of the non-stationarity, it means that the observations actually become more important to us rather than less important, because we cannot assume that they're going to continue to have the same statistical properties. I want to say a couple words about Dave Keeling, who was the scientist who said we need to measure the CO2 in the global system, and he did this at the summit of Mauna Loa Observatory, creating this site, a brilliant move on his part to measure this absolutely important signal. And this is a piece of Keeling's Mauna Loa CO2 record. Down at the bottom, by the way, is a graph of the funding history for his efforts, because agencies kept starting and stopping funding him because they all said, this isn't research, this is just data collection, where's the science, etc. And yet this is the science and the data set and the science that helped us really understand the way the whole planet really breathes in terms of oxygen and carbon dioxide. The most important environmental record that we have in the world. Charlie Vorismarty likes to say, and I do too, that we hydrologists, we have CO2 envy. We wish we had records that were as clean and clear as this one, describing the nature of the change that is going on in the system that we're interested in. Just a quick progression from this incredibly clean, clear statement about global CO2. This is a record from Amherst, Massachusetts, done by folks at the University of Massachusetts from a poster of theirs. This is the temperature record in Amherst. It's not as clear as the global CO2 record, but the upwards trends are undeniable. But then we could move to a water environment. This is the Connecticut River of Thompsonville, Connecticut, just by the Connecticut-Massachusetts state line, a data set that runs back to around 1930. And we can see some slight trends in the mean daily and maybe the minimums, but the signal is not nearly as clear. And I think the hydrologic signals will never be as clear as the temperature signals are. And this is a real challenge to water science, how difficult it is to really tease out what's going on as a result of increased greenhouse forcing. So to end with sort of some philosophical things, this is a quote from Ralph Keeling, the son of David Keeling, who wrote a piece in Science called Recording Earth's Vital Signs, which was a sort of a mini biography of his father's career. And Ralph Keeling said, the only way to figure out what is happening to our planet is to measure it, not model it, but measure it. And this means tracking changes decade after decade. And we often find people thinking that you can say something about trend by looking at a decade or two, and my answer is it doesn't mean anything if it's over a decade or two. You really have to look long term. And then finally, and this is critical, is poring over the records. The answers are not going to jump out at you. You really have to apply a lot of effort to get at what's actually going on and to try to learn from the record. And in fact, even as clean and clear a record as Dave Keeling had for global CO2, he delved into it in enormous detail and learned a whole lot of things about the whole global biogeochemical cycle. So how to build a bridge. I've got sort of a number of statements to sort of make in conclusion. First of all is collect the data decade after decade. Be persistent about the collection of data. Pore over the data for the signals and try to describe what those signals are. Use the data to test models. Got to bring both sides together, the empirical and the deterministic. And we need to use decision frameworks that recognize deep uncertainty. It's not just, oh, well, we don't know the mean exactly, we don't know the standard deviation exactly. It's really, we don't know what's happening to this process overall, and we need to be prepared for things to look very different in the future than they have in the past. The next point is what I call avoid arrogance and avoid paralysis. The arrogance is people who will tell you, oh, I know what the outcomes of greenhouse warming will be in terms of the flows of these rivers. I don't think we're anywhere near a position to answering those questions. And we need to temper our language to make people understand just how little we know about those kinds of things. But we also need to avoid paralysis, and that is, well, since we don't know what's going to happen, we're just going to behave as if nothing's happening, nothing's changing at all. And it's a difficult line to walk, and I think all of us in this community who deal with these issues are still sort of feeling our way through that problem. Build resilient plans and operations. The future may be well outside our envelope of experience, so we need to be prepared to see things happen, whether they be droughts, whether they be floods, things that we've never seen before, even if we have, say, 100 years of record. And finally, use diverse portfolios and be adaptive. Diverse portfolios meaning get your water from multiple places, not just one reservoir, but multiple reservoirs. Use the groundwater system. The diversification can provide a lot of protection from the unexpected. And be adaptive. And what does adaptive management mean? Adaptive management absolutely depends on having observations of how the system is behaving and continually, ongoing, doing repeated analysis to feed back to the operational decisions. So you all have a, you know, I entered this field, this profession, when we were all comfortable with the stationary world. You're entering it when we recognize a non-stationary world, and you've got a much tougher job ahead of you, trying to find a way that we cross that bridge from the world of a stationary mindset to a more realistic non-stationary mindset. We probably don't have time for questions. I don't know. I think we're getting right up against the edge, but I thank you for your attention. I'll be here all through today and through the end of the meeting tomorrow. I love coming to meetings like this and hear what people are working on and new ideas, et cetera, and I'm happy to entertain your questions.
Thank you.
Thank you, Dr. Hirsch, for that wonderful talk. Very captivating. So that concludes our opening session. We'll have a 15-minute break till 10 a.m. and then the first technical session start. There is some refreshment and coffee in the lobby in Marcus Hall if you'd like to help yourselves. Thank you for attending and seeing the sessions.
We got them here.